Something is watching from below. Not from the shallows where light still reaches. Not from the mesopelagic twilight where the last grey traces of the sun thin out and vanish. From 1,000 meters beneath the surface of the Southern Ocean, in water barely above freezing, and darkness so complete it has never known a photon of sunlight. Something the mass of a large adult human drifts in the water column. It turns slowly. It opens its eye. That eye is roughly the size of a dinner plate. Its diameter is the largest confirmed in any living animal on Earth. At the center of that eye, embedded deep in the iris like a lamp set behind a window, is a small organ that produces its own cold, blue light. The light is not for display. It is the eye illuminating itself from within, a biological structure that allows this creature to detect the faint, bioluminescent flashes of whatever approaches in the surrounding dark. The creature is the colossal squid. It is the largest invertebrate on the planet by mass. It carries rotating hooks on its tentacles, hooks that swivel like ball and socket joints, designed to grip prey so that no direction of struggle will release it. Its beak can sever the spine of a deep-sea fish. It has shared this ocean with us for millions of years, and we have never seen one alive in its own environment. It comes to us only dead or dying, hauled up by accident in the nets of fishing vessels targeting other prey, or recovered piece by piece from the stomachs of sperm whales, a handful of beaks and tentacle fragments and hooks that told us something vast was down there, before we had any real picture of what that thing looked like. Tonight we are going down to find it. This is not a journey into fear, though the colossal squid has been borrowed by every mythology that needed something vast and tentacled lurking below the surface. This is a journey into something stranger and more patient than fear. It is a journey into one of the last genuinely unknown animals on Earth, a creature that outmasses every other invertebrate in the ocean, and that has kept its essential life completely hidden from us. The eye is still down there, still open in the dark, still watching whatever approaches. If you find this slow, quiet exploration of mystery something you genuinely enjoy, I'd be grateful if you'd like the video and subscribe. Letting me know in the comments where you're listening from and what time it is for you is always a quiet comfort. Now find your comfortable position, dim the lights, take a slow breath. We are leaving the map behind. The Southern Ocean keeps its animals well. It has more secrets per square kilometer than any other body of water on the planet. Its depth and cold and distance and storm have conspired for the entire history of human exploration to hold its most significant residents out of our sight. We have crossed it in wooden ships and steel ones. We have lowered instruments into it on cables kilometers long. We have sent robots down to its floor, and yet the animal that holds the record for the largest eye in the history of animal life on this planet has never been photographed alive in its own habitat. That eye is open right now, in the dark, in the cold, at a depth that would kill us in seconds, watching for something in the bioluminescent dark with an instrument that evolution has spent millions of years perfecting. We are going to get as close as we can. For most people, the monster that lives in the deep ocean has one name: the giant squid, Architeuthis dux, the kraken, the many-armed thing that coiled around sailing ships in the fever dreams of sailors and in the elaborate illustrations of 19th century naturalists who had never seen one but felt they understood it. That creature is real. It lives in deep water across the world's oceans. Its longest tentacles can extend to 13 meters from tip to mantle. It is genuinely large, genuinely strange, and it took us until 2004 to photograph one alive in the open ocean. But the colossal squid is not the giant squid. They are different animals entirely. Different genus, different anatomy, different ocean. The giant squid, our Architeuthis, is the record holder in length. The colossal squid, Mesonicoteuthis hamiltoni, is the record holder in mass. One is a record in reach, the other in weight, and mass is the better measure of a creature's physical reality. The colossal squid has more substance to it than any other invertebrate on record. More muscle, more organ and biochemistry, more body pressing against the water that surrounds it. Most people have never heard of it. This is the first strangeness we encounter. There exists an animal heavier than any invertebrate we have catalogued, and it has no popular mythology. The giant squid has its legends, its Victorian woodcuts, its appearances in literature and film. The colossal squid has only science, and science has had very little material to work with. No naturalist illustrated it for popular magazines in the 1800s. No sailor's ghost story mentioned it by name. It waited in the Southern Ocean, heavier than the legend, completely unaware of the legend, entirely unhurried. The species was formally described in 1925 by the British zoologist Guy Coburn Robson, based on a pair of tentacle clubs recovered from the stomach of a sperm whale taken in the South Atlantic. He gave it the genus name Mesonicoteuthis, meaning roughly the middle claw squid, for the rotating hooks he found on those clubs. For decades after that, the species was known only from fragments. A tentacle here, a beak there, hooks preserved in alcohol in museum jars. An animal assembled from its own scattered wreckage. What we pictured in those decades was probably wrong. The whole animal, it turned out, was stranger than the parts suggested. The colossal squid kept its secrets. It still does. But the map of what we know has, slowly and with great difficulty, been growing larger. The distinction between the two species runs deeper than size. The giant squid, Architeuthis, is a global animal. It has been recovered in waters across the world's oceans, from the North Atlantic to the South Pacific. It lives at depth but ranges widely. Its population is distributed across a vast area, which is part of why it accumulated more encounters with human beings and more entries into human mythology. Wherever people went to sea and went deep, Architeuthis eventually surfaced into their world. Mesonicoteuthis hamiltoni is an endemic species. It belongs specifically to the deep waters of the Southern Ocean. It does not range widely. It is not found in the North Atlantic, or the North Pacific, or the Indian Ocean, or anywhere else, except the cold waters that surround Antarctica. This geographic confinement is part of its obscurity. The people who work the Southern Ocean are a small subset of the world's fishing fleets, and a small subset of the world's scientists. The Antarctic waters are difficult to access, expensive to work in, and inhospitable to the kind of sustained observation that builds public knowledge about a species. The colossal squid is the apex invertebrate of the deep Southern Ocean, and most people have heard its name, if they have heard it at all, only as a footnote to a documentary about something else. The world has a map. On that map, the colossal squid occupies a circle around the bottom of the globe, deep beneath waters that most people will never see. The map labels it but the label is very nearly all the map gives. To understand the colossal squid, we must first understand where it lives. And to understand where it lives, we must understand the ocean that surrounds it. The Southern Ocean is the body of water that rings Antarctica. It is the only ocean that circles the entire planet, connecting the Atlantic, the Pacific, and the Indian Oceans in one vast, unbroken loop. It has no continental landmass to interrupt it, no land boundary to the south, except the ice sheet of Antarctica itself. And this absence of interruption is the key to its character. It moves constantly, relentlessly, driven by winds that have been blowing with nothing to stop them for millions of years. The Antarctic circumpolar current is the strongest ocean current on Earth. It carries more water than any other current, more than 100 times the combined flow of all the world's rivers. It moves from west to east in a permanent procession, and it separates the cold, polar water of the deep south from the warmer water of the sub-Antarctic latitudes. This boundary, where the cold water sinks beneath the warmer water, is called the Antarctic convergence. It is one of the most productive biological boundaries in the ocean, a place where nutrients well up from the deep and support enormous populations of krill, fish, seabird, whale, and squid. The colossal squid lives south of that convergence, in the frigid zone, in the Ross Sea, in the Weddell Sea, in the waters that surround the continent of ice at the bottom of the world. The conditions are extreme by every measure we use to describe extremity. Water temperatures near the surface hover between minus 1.8 and 2 degrees Celsius, and at depth they are colder still. Storms in the Southern Ocean are legendary among mariners. The winds in the latitude bands, known as the Roaring Forties and the Furious 50s and the Screaming 60s, circle the planet without interruption, building swells that can reach 20 meters in height. Research vessels operating in these waters are purpose-built for punishment, and they still sustain damage on the rougher crossings. The colossal squid does not experience the surface of this ocean. It lives at depths of 600 to 2,000 meters, in water where temperature changes very little with depth, and where the surface violence above is a distant and irrelevant fact. But the ocean that produces those storms is the same ocean that shapes the deep ecosystem the squid inhabits. The nutrient cycles and current patterns and the populations of every creature the squid preys upon, all of these are products of a southern ocean defined by cold and wind and uninterrupted circulation. The fortress that guards the colossal squid is not just darkness and depth. It is also geography. To reach its habitat, you must cross one of the most difficult stretches of open ocean on the planet. The squid lives in the last truly remote place. Even if you could cross the Southern Ocean without being broken by it, the depth is waiting. The colossal squid spends most of its life at 1,000 to 2,000 meters below the surface. This zone is called the Barth Epipelagic, from the Greek word for deep. It is a zone of permanent darkness. No sunlight reaches it. The only light that exists here is produced by the creatures themselves, cold flashes and pulses of bioluminescence moving through water that has never known day or night as we understand those terms. At 1,000 meters, the pressure is roughly 100 times the pressure at the surface. Place a sealed aluminum can at that depth, and it crumples instantly, a small violent implosion of metal. Place a human body at that depth, without protection, and the lungs collapse, the ears rupture, the nitrogen in the bloodstream becomes lethal. The body, as we are designed, does not belong here. Every organ we carry was built for atmospheric pressure. At 1,000 meters, that pressure becomes the definition of impossible. The colossal squid is built differently. It has no air-filled chambers to be crushed. Its body is largely composed of water and the gel-like tissue of its mantle and organs, which are essentially incompressible. What would destroy us passes through it. The pressure that makes this zone inaccessible to us is simply the normal condition of its life. The cold is absolute. Water at these depths in the Southern Ocean sits near 1 degree Celsius, close to the physical limit, where seawater remains liquid rather than ice. This cold is not temporary. It does not cycle with seasons the way surface water does. It has been this temperature for a very long time. The colossal squid has evolved in it, for it at every level of its biology. Its enzymes function at temperatures that would freeze the biochemical processes of most surface creatures into inactivity. What we have, then, is an animal that thrives precisely where we cannot go. Too deep for our bodies, too cold for our physiology, too dark for our eyes. The instruments we use to study other ocean environments work poorly in the deep Southern Ocean, where severe weather limits deployment and recovery, where currents can pull equipment kilometers off course. There are places on Earth we know less well than we know the surface of Mars. The deep Southern Ocean is one of them. The colossal squid lives there, and it gives very little away. There is another dimension to this inaccessibility that is easy to underestimate: the weather above. Most of what we know about the deep ocean has been gathered by research vessels that lower instruments on cables, deploy remotely operated vehicles on tethers, and collect water samples and sediment cores through operations that require the vessel to hold a stable position for hours or days at a time. In the Southern Ocean, stable position is a luxury that the weather refuses to grant reliably. The average wind speed in the water south of the Antarctic convergence is among the highest in the ocean. Storms develop quickly and move fast. A vessel that begins a deployment in manageable conditions can find itself in seas that make retrieval dangerous within a few hours. Equipment is lost. Operations are abandoned. The windows of calm that allow sustained scientific work in these latitudes are narrow and unpredictable. This means that the research effort that has been applied to the deep Southern Ocean is a fraction of what has been applied to more accessible ocean regions. The Monterey Canyon off California and the deep trenches of the tropical Pacific, and even the Mariana Trench, have all received more sustained robotic attention than the bathypelagic waters of the Ross Sea, where the colossal squid lives. Getting there is hard. Staying there is harder. Getting instruments down to depth and back without losing them is harder still. The colossal squid did not choose its home for the difficulty it poses to researchers. It chose its home over millions of years of evolution because the conditions there supported its life. But the effect is the same. The animal lives inside a natural fortress. The walls of that fortress are storm and ice and depth and cold, and those walls have, so far, held. The first proof that the colossal squid existed did not come from any ocean expedition. It came from the stomach of a dead whale. Sperm whales have been hunted by humans for centuries. They were hunted for the waxy oil in their enormous heads. the spermaceti, which burned cleanly in lamps and lubricated the precision machinery of the Industrial Revolution. They were hunted in the Southern Ocean with particular ferocity in the 19th and early 20th centuries, and when whalers processed a whale, they sometimes opened the stomach and found things there that had no clear explanation. The beaks were the main evidence. Squid have hard beaks made of chitin, shaped something like a parrot's bill, but flipped 90 degrees. Unlike the soft tissue of the squid's body, the beak does not digest easily. It accumulates in the sperm whale's stomach, hundreds or thousands of beaks from hundreds or thousands of squid consumed over years. Whalers who cut into sperm whale stomachs in the deep Southern Ocean found beaks unlike any they had seen before. Larger, heavier, the upper beak of a large Architeuthis, a giant squid, was already known to science and was itself formidable. But these other beaks were different in shape and significantly larger. Something was down there that was not the giant squid. This was not a dramatic revelation at the time. It was more of a quiet taxonomic puzzle, noted by a few researchers and then filed away. The beaks were collected and described and placed in museum drawers. No one mounted an expedition to find the animal they implied. The Southern Ocean was not a place you went looking for one specific squid species. It was barely a place you went at all unless your business required it. Over the following decades, as industrial whaling continued and whale stomach contents were occasionally catalogued with care, more of these unusual beaks accumulated. The hooks appeared too, the rotating hooks that Robson had described from his 1925 specimen, recovered from other whale stomachs, and occasionally from the sea surface, when the stomach contents of a dead or dying whale were strewn across the water. The picture of an unknown animal assembled itself, one recovered piece at a time. What no piece of evidence told us was what the whole animal looked like, alive in the water, doing what it actually did in the dark. That picture would take decades more to arrive. When it finally did, it arrived entirely by accident. The history of discovering deep ocean animals through the stomach contents of other animals is longer and stranger than most people realize. Before remotely operated vehicles and deep-sea submersibles and hydrophones, the stomach was the archive. Whalers were the inadvertent first deep-sea biologists of the Southern Ocean, and the records they kept are the foundation on which later researchers built their understanding of what lives at depth. The problem with using a sperm whale stomach as a scientific instrument is obvious. The whale processes its meals. Soft tissue dissolves. Bones are digested or regurgitated. What remains is what is chemically resistant enough to survive that environment. Beaks and hooks, certain hard structures, the occasional fossilized remnant of a meal eaten long ago. Soft tissue information is almost never preserved. The animal that produced a given beak can be measured and classified by the beak alone, but it cannot be seen or understood as a whole living creature from the beak alone. This is the limitation that shaped our knowledge of the colossal squid for nearly a century. The animal existed in the scientific record primarily as a collection of hard parts, removed from the bodies of dead whales by men who were primarily interested in the whales. The squid itself was inference, large, hook-bearing, Southern Ocean, deep. The living animal was a shape drawn around a handful of curved chitin pieces, and the shape changed every time a new piece was found. In 1925, the British Museum received a pair of tentacle clubs recovered from the stomach of a sperm whale taken in the South Atlantic. The clubs were strange. They bore not suckers, as the giant squid's tentacle clubs do, but hooks, rotating hooks, set in sockets so that they could swivel freely. The zoologist, Guy Coburn Robson, examined them and concluded they represented a new genus entirely. He named the species Mesonychoteuthis hamiltoni, the middle claw squid. The species name honoured the Scottish naturalist William Rowan Hamilton, who had contributed to the scientific effort in the region, and with that description, published in a specialist journal that almost no one outside of malacology would ever read. The colossal squid entered the scientific record. It then largely disappeared from it. For more than 50 years, almost nothing new was added to our knowledge of Mesonychoteuthis hamiltoni. The species was real, the hooks were real, but the animal remained a phantom assembled from fragments. There were occasional recoveries of additional material from whale stomachs. There was some effort to estimate the animal's size based on the hook dimensions and the relationship between hook size and body size in known squid species. Estimates range from large to very large, but without a whole animal. The estimates were speculation layered on inference. The first significant step forward came in 1981. A Russian research vessel operating in Antarctic waters recovered a squid that the crew recognized as something unusual. The specimen was relatively small, a juvenile, but it was identifiably Mesonychoteuthis hamiltoni. It was the first time anyone had held a reasonably complete specimen of the species in their hands. The mantle was roughly 1 meter long. The hooks were present and matched the description from 1925. The animal was preserved and described, and the scientific community's understanding of what the colossal squid actually was took one small step out of the darkness. Over the following 2 decades, more specimens arrived. None of them were intact adults. They came from fishing bycatch in the Ross Sea, from the waters of the Weddell Sea, from the stomachs of toothfish brought up on long lines. Fragments, partial animals, a mantle without arms, a head without a mantle. Each specimen added something to the picture, while leaving the larger picture incomplete. The colossal squid was real. That much was now beyond question. But what a full-grown adult looked like, and how it behaved, and how it spent its life in the deep, all of that remained as dark as the water it inhabited. To understand what the colossal squid is, we need to understand what a squid is, because the colossal squid takes the squid body plan and does something extraordinary with it. All squid belong to a class of mollusks called cephalopods, which means head-footed, the animals whose feet have evolved into arms radiating from around the head. The cephalopods include octopuses, nautiluses, and cuttlefish as well, but squid occupy a particular ecological role. Fast-moving, jet-propelled, often schooling, often prey as much as predator. The colossal squid shares this heritage, but occupies it at a scale that changes almost every assumption about what a squid is. The mantle is the main body of the squid. In the colossal squid, the mantle is a broad, muscular cone, thicker and shorter in proportion than the mantle of the giant squid. The largest confirmed adult mantle length on record is roughly 2.5 meters. The total length, including arms and tentacles, is harder to determine, because tentacles are frequently retracted or damaged in recovered specimens. but estimates for large adults range from 7 to 12 meters. The mass is where the record sits. The largest confirmed specimen, examined in New Zealand in 2008, weighed approximately 495 kilograms. That is roughly the weight of a large male brown bear, concentrated into a single animal with 8 arms and 2 longer tentacles, and a razor-edged beak, and the largest eye in the animal kingdom. Running through the interior of the mantle is the gladius, a transparent or pale amber blade of chitin that gives the mantle its structural rigidity. It is the squid's internal shell, evolved from the outer shells of ancient ancestors into something lighter and internal. In the colossal squid, the gladius is broad and stiff and runs nearly the full length of the mantle. It resembles a large quill pen pressed flat. It is one of the more eerie things to hold. Something that looks like amber glass shaped into a feather, pulled from the interior of an animal that was enormous in every measurable way. The fins extend from the rear of the mantle like 2 large lobes of muscle. Unlike the slender tail fins of the giant squid, the colossal squid's fins are wide and rounded, occupying a large portion of the mantle's length. They are used for slow, precise maneuvering rather than rapid propulsion. The colossal squid does not chase its prey the way a sleek, streamlined predator might. It is built for something else entirely, something we will come to in a moment. The beak sits at the center of the arm crown, where all 8 arms converge. It is hard and hooked and dark and large enough in a full-grown adult to make the beak of a giant squid look modest. It can slice through the flesh and bone of a deep-sea fish with the efficiency of a pair of bolt cutters. The beak is one of the things, along with the hooks, that makes the colossal squid something more than simply a very large squid. It is built to hold. It is built to cut. It is built for a life of encounter in the dark. Among the things that make the colossal squid genuinely unlike anything else in the ocean, the hooks stand out with particular clarity. Most squid species use suckers on their arms and tentacles to grip prey. The suckers of the giant squid are themselves formidable, circular rings of chitin with serrated edges, like small circular saw blades, which cut into the flesh of whatever the tentacle grips. But the colossal squid has taken a different path. Its tentacle clubs, the expanded pad-like sections, at the end of the 2 longer tentacles, are lined with hooks. Not fixed hooks, but rotating ones. Each hook sits in its own socket and can swivel freely in almost any direction. There are also shorter hooks on the suckers of the 8 regular arms, though these are fixed rather than rotating. The rotating hook is a mechanical solution to a specific problem. When any gripping limb encounters a struggling prey animal, the struggle tends to loosen the grip. The prey twists. The tentacle must twist with it or lose contact. A sucker maintains its grip only if the sucker's axis aligns with the direction of pull. A rotating hook, set in a free-moving socket, can maintain its grip regardless of which direction the prey moves. The hook engages into the flesh, and then the prey's own struggle drives it deeper. There is no direction of movement that helps the prey escape. Think of what that means for an animal that encounters prey at 1,000 meters in total darkness with no possibility of a second attempt. If the squid is an ambush predator, and the evidence strongly suggests that it is, then each strike must be definitive. The hooks make it definitive. They are not a tool for the beginning of a struggle. They are a tool for the end of one. The hooks on the tentacle clubs of the largest specimens are large enough to be clearly visible to the naked eye, curved and pale and sharply pointed, set along the club in 2 rows. Researchers examining thawed specimens have described them as resembling the blade of a linoleum knife, that particular inward curve that is designed not just to pierce but to hold. The comparison is mechanical rather than dramatic, which is more unsettling than drama in its own way. There is nothing theatrical about these hooks. They are functional in the coldest, most efficient sense of the word. The Antarctic toothfish is the colossal squid's primary known prey. The toothfish, also marketed under the name Chilean sea bass, can grow to lengths of more than 2 meters and weights exceeding 100 kilograms. When a toothfish is recovered on a long line in the Ross Sea and shows signs of squid predation, the marks on its body are unmistakable. Paired rows of circular wounds from the hooks, sometimes the beak marks, where the squid was in the process of feeding when the line pulled the fish toward the surface and disrupted the meal. Several confirmed colossal squid specimens were caught this way, feeding on hooked toothfish, brought up with their prey still in their grasp, the hooks held, even at the surface, even in bright light and noise, and the confusion of being hauled into a world utterly unlike their own. The colossal squid held on. We return now to the eye, because the eye is the thing that the colossal squid carries that no other animal on Earth carries, and it deserves more than the brief mention it received in the opening. The diameter of the largest confirmed colossal squid eye is approximately 27 centimeters. 27 centimeters is roughly the diameter of a volleyball. The eye of a large blue whale, the largest animal alive, reaches about 15 centimeters. The eye of a human being reaches about 2.5 centimeters. The colossal squid's eye is more than 10 times wider in diameter than our own. Eyes do not grow to 27 centimeters for cosmetic reasons. They grow that large because large eyes collect more light. The relationship between eye size and light gathering capacity is straightforward. A larger lens captures more photons per unit of time. In an environment where light is vanishingly rare, where the only photons available are the cold blue-green flashes produced by living organisms, a larger eye is a more sensitive eye. It picks up signals that a smaller eye would miss entirely. At the depths where the colossal squid lives, nearly everything that moves produces some form of light. The bioluminescence of the deep ocean is not decorative. It is communication and predation and defense and luring and camouflage all at once. Small creatures flash to warn others of danger. Predators lure prey with lights. Prey animals startle predators with sudden bursts of blue-green fire and then flee in the confusion. In this world, seeing even the faintest light is survival. But the colossal squid may be using its eye for something more specific. Deep in its iris there appears to be a light-producing organ of its own, a photophore embedded in the eye itself. The leading hypothesis is that this internal light source allows the squid to illuminate its own visual field at very close range, the way a diver's headlamp illuminates what is immediately in front of the diver. The squid carries its own light source in its own eye, pointed inward and forward, a biological torch integrated into the very structure through which it sees. There is another hypothesis, one that is harder to verify, but that carries a particular elegance. Sperm whales are large and dark. When they swim through bioluminescent water, they disturb it, triggering flashes in the plankton and small organisms around them. A whale moving through the deep water column at speed leaves a trail of disturbed bioluminescence behind it, like the wake of a ship lit up in cold fire. An eye large enough to detect that wake, to see the phosphorescent disturbance of an approaching predator, long before the predator itself comes into visual range, would provide an enormous survival advantage. The colossal squid may not be watching prey with that eye. It may primarily be watching for the thing that hunts it. The eye gives nothing away, but the more we understand about how it is built, the more the darkness it peers into begins to make sense. Here is a paradox. The colossal squid is the largest invertebrate on Earth by mass. It is also, by the best available evidence, one of the more metabolically sluggish large animals in the ocean. For most of us, the image of a large predator is an active one. Size implies power. Power implies speed. Speed implies pursuit. The great white shark cuts through water at more than 50 kilometers per hour in a burst. The sperm whale drives downward at 2 meters per second, descending more than a kilometer in under 10 minutes. Large predators, in the popular imagination, are fast. The colossal squid appears to be different. Its body plan suggests slow, deliberate movement, rather than rapid pursuit. The wide, rounded fins are designed for stability and precision at low speed, not for propulsion. The jet propulsion system that all squid use, drawing water into the mantle cavity and expelling it through a flexible siphon, is present in the colossal squid. But the mantle is proportionally broader and shorter than in swift, streamlined squid, built for speed. The muscle tissue of the colossal squid, analyzed in laboratory conditions, suggests a metabolic rate that is low relative to the animal's mass. What does a low metabolic rate mean for a life in the deep? It means the animal needs less food to sustain itself. It means it can wait longer between meals without deteriorating. It means the strategy of sitting very still in very cold water, waiting for prey to come to it, is a viable one. Perhaps the most viable one available at this depth and in this cold. The colossal squid, the best evidence suggests, is an ambush predator. It does not cruise the dark water searching actively for toothfish. It drifts, it waits. When something large enough comes within range, it strikes. The strike itself is presumably rapid. The hooks on the tentacle clubs require contact to engage, and contact requires a fast extension of the tentacles. In many squid species, the tentacles can extend at extraordinary speed, too fast for high-speed cameras to capture in full detail. The colossal squid's tentacle strike has never been observed directly, but the tentacles themselves are long and powerful, and the hooks are arranged to engage on impact. The strike is probably the one fast thing in an otherwise slow and patient existence. This makes a kind of ecological sense. Cold water suppresses metabolism. Low metabolism means lower energy requirements. Lower energy requirements mean the squid does not need to spend vast amounts of energy hunting actively. It can afford to be still and suspended in the dark, conserving its resources for hours at a time. The animal that looks from the outside like a massive aggressive predator is in its internal economy something more like a patient monk, still, quiet, waiting for the world to come to it. The world eventually does. The sperm whale is the largest toothed animal on Earth. A large adult male can reach 18 meters in length and weigh 57 metric tons. Its head accounts for roughly 1/3 of its total body length, and inside that head is the largest brain of any animal alive, and the largest biological sonar system in the known world. The sperm whale's echolocation clicks are the loudest biological sounds produced by any animal, concentrated beams of sound that can stun or disorient prey at range. The sperm whale dives for the colossal squid. There is no other way to state this that does not diminish the strangeness of it. The largest toothed predator on Earth descends more than a kilometer into Antarctic waters in complete darkness and near freezing cold, holding its breath for up to 90 minutes to hunt an invertebrate that may weigh half a ton and whose tentacle hooks leave scars. The scars are real. The skin of sperm whales hunted in the Southern Ocean and in other deep water zones, where large squid live, frequently shows circular suction cup marks and hook wound scars that are clearly the products of squid tentacles wrapped around a whale's body. The diameter of some of these scar rings exceeds 40 centimeters, larger than any sucker or hook found on any confirmed Architeuthis specimen, and consistent with Mesonicoteuthis hamiltoni at the larger end of estimated adult sizes. What these scars describe is an encounter, not a struggle between predator and prey in the ordinary sense, where one pursues and the other flees, but something that happens in the dark at great depth between two animals of extraordinary and nearly equal capability. The sperm whale has its sonar and its size and its speed. The squid has its hooks and its size and whatever advantage comes from living in water. It has known since birth. At temperatures the whale must constantly warm itself against. The whale wins most of these encounters. This we know because the beaks accumulate in whale stomachs. A single sperm whale stomach has been found to contain more than 10,000 squid beaks. Not all of these would be colossal squid, but many are. The scale of the accumulation suggests that sperm whales in the Southern Ocean eat colossal squid with some regularity, not as an occasional prize, but as a meaningful portion of their diet. But the squid does not always lose. Whales have been found with injuries that suggest the squid fought back with force. A whale that is enveloped by the tentacles of a large Mesonicoteuthis hamiltoni has 200 hooks engaged in its flesh, any of which can rotate to deepen its grip in response to the whale's movement. The outcome of that encounter in the absolute dark at 1,000 meters is not a foregone conclusion. We have never seen one of these encounters. We may never see one. They happen in the most inaccessible place on the planet, between two animals that live most of their lives beyond any instrument we have yet managed to deploy reliably in that environment. But the evidence of them is there in the bodies of the whales, written in circles of scar tissue on skin that has surfaced briefly into our world before disappearing below again. The squid gives nothing away, but the whales carry the record of the meetings in their flesh. In early February of 2007, the New Zealand fishing vessel San Aspiring was working the deep waters of the Ross Sea, setting long lines for Patagonian toothfish. Patagonian toothfish, marketed under the name Chilean sea bass, are large and valuable and deep living. Fishing for them requires long lines set at depths of up to 2,000 meters, lines bearing hundreds of baited hooks strung along a length of cable that can stretch for several kilometers. When the long line is hauled in, each hooked fish is retrieved and processed on deck. It is slow, cold, difficult work in difficult water. When the crew of the San Aspiring began hauling in one of their long lines that morning, they noticed something unusual at the end of it. One of the toothfish had company. Wrapped around the toothfish, its tentacle hooks engaged in the fish's flesh, was the largest squid any of them had seen. The squid was still alive. It was feeding on the toothfish, even as the line brought both animals slowly up from depth. The crew did not release it. They brought the squid aboard as well. What they had on their deck was an adult female colossal squid, in better condition than any previously recovered specimen, still intact, the arms and tentacles present and undamaged, the mantle not torn or compressed. She was 10 meters long from the tip of her mantle to the ends of her tentacles. She weighed approximately 495 kilograms. The New Zealand Ministry of Fisheries was notified. The squid was frozen whole and transported to Wellington, where it was received by the Museum of Te Papa, Tongarewa. For the following 14 months, the frozen specimen was held while a team of scientists planned the examination. The process of studying a frozen animal of this size requires preparation, specialized equipment, and patience. You cannot simply thaw it and proceed. In April of 2008, in a tank specially constructed to hold and support the thawed animal, the examination began. The team was led by Steve O'Shea, a squid specialist at what was then AUT University in Auckland, along with colleagues from Te Papa and from international institutions who had come specifically to participate. Working over the course of 10 hours, they measured and photographed and sampled and documented every part of the animal. The eye was removed from the head with great care and measured, 27 centimeters in diameter. The lens alone was the size of an orange. The chromatophores, the pigment cells that allow squid to change color and pattern rapidly, were visible in the mantle skin even after months of freezing. The beak was extracted and weighed. The gladius was pulled from the interior of the mantle and laid out beside the animal. It was longer than a person is tall. The scientists worked quietly and methodically in a room that smelled of the cold and of the sea, and of something harder to name, some quality of the animal itself that the freezing had preserved along with its shape. They were the first people to have a full-grown adult female colossal squid in front of them, with the time and the instruments to examine her properly. She gave them what she could. The gaps she left behind were, as always, larger than what she gave. There is something strange inside the flesh of the colossal squid that explains in part why it has never been targeted as a commercial food fish, and why even its primary predators must cope with eating it in large quantities. The flesh is saturated with ammonium chloride. Cephalopods face a buoyancy problem that fish do not. Fish maintain their position in the water column using a swim bladder, a gas-filled sac that can be inflated or deflated to match the density of the surrounding water. Squid lack this structure. A squid's body is denser than seawater. Without some compensating mechanism, it tends to sink. To achieve neutral buoyancy, without a gas bladder, some squid species have evolved a different solution. They accumulate ammonium chloride in their tissue fluids. Ammonium chloride solution is less dense than seawater. By saturating their tissues with it, squid can achieve near neutral buoyancy. hovering in the water column without the constant muscular effort that sinking would otherwise demand. The colossal squid relies on this mechanism heavily. Its flesh, tested in the specimens that have been examined, is thoroughly permeated with the compound. The concentration is high enough that the flesh of a colossal squid tastes strongly and unpleasantly of ammonia, or of something close to ammonia, acrid and sharp and deeply wrong on the human palate. This is why the colossal squid is not fished commercially. There is no market for something that tastes like household cleaner. The fishing vessels that occasionally haul up a colossal squid as bycatch from their toothfish operations have no economic reason to retain it, and every sensory reason not to. The largest invertebrate in the ocean is, from a commercial food perspective, worthless. The evolutionary logic here is worth noting. An animal that accumulates ammonium chloride in its tissues achieves buoyancy, but it also becomes unappealing to a wide range of potential predators. Most fish that encounter a squid-flavored piece of bait in experimental settings will not touch it if the ammonia concentration is high enough. The colossal squid has, in effect, made itself inedible to the vast majority of the predators that might otherwise attempt it. The sperm whale is an exception. Sperm whales eat colossal squid in enormous quantities, and the ammonia content appears to present no obstacle to them. Their digestive systems are clearly adapted to process it. But sperm whales aside, the ammonia body is a form of passive defense, an entire chemical fortress built into the flesh of an animal that already carries rotating hooks and a beak strong enough to cut bone. The colossal squid is a creature that did not want to be eaten, and except by one specific predator, it largely succeeded. Despite everything we now know about the colossal squid, the list of what we do not know remains far longer than the list of what we do. We have never seen mating behavior. We do not know where or how the colossal squid reproduces. We have no confirmed egg masses. We have no confirmed newly hatched juveniles. We cannot say with certainty how quickly they grow from hatchling to adult, how long they live before they reach full size, or how many years a large adult has lived when we encounter one. The males are another mystery. The sexual dimorphism in the species is extreme. Females grow much larger than males, which is common among cephalopods, but in the colossal squid reaches a point where the male and female animals are so different in size that for many years researchers were uncertain whether the small male specimens being recovered were actually Mesonychoteuthis, Hamiltoni, or some other species. The male colossal squid is substantially smaller than the female, reaching mantle lengths of perhaps 1 meter compared to the female's 2.5. This means that in any population of colossal squid, the males are simply much harder to detect. They require a smaller prey to sustain themselves, and occupy perhaps a different vertical range in the water column. We do not know how males find females in the dark. We do not know what finding looks like at these depths. The lifespan question is particularly difficult. Most cephalopods live short lives relative to their size. Octopuses rarely live more than 2 or 3 years. Giant squid are estimated to live perhaps 5 years at the outside. If the colossal squid follows a similar pattern, then the animal that weighed 495 kilograms on the deck of the San Aspiring in 2007 was perhaps 3 or 4 years old. It grew to the weight of a brown bear in roughly the time it takes a human to complete primary school. If that growth rate estimate is correct, and it is at best a well-informed guess. Then the colossal squid grows faster than almost any animal of comparable mass on Earth. The metabolic logic seems contradictory. A slow metabolism ambush predator that also grows at a rate that implies enormous energy investment. The resolution may lie in the diet. Patagonian toothfish are energy-dense prey. A single large toothfish represents a substantial caloric investment. A colossal squid that consumes one large toothfish every few days in its early life would have the fuel for rapid growth, even at a relatively low metabolic rate. But this is inference piled on inference. We do not have growth data from living animals observed over time. We do not know what a young colossal squid eats in its first months of life. We do not know the size at which it begins hunting toothfish, rather than smaller prey. We do not know, really, where the juveniles are. The most abundant large invertebrate in the Southern Ocean, an animal that sperm whales depend on as a primary food source, and that may exist in populations of millions of individuals, has successfully hidden its entire developmental life from us. We have never watched a colossal squid grow. We have only ever found it fully formed, already enormous, already complete. Everything before that is still dark. The Southern Ocean is changing. The Antarctic circumpolar current, that great loop of moving water that has defined the conditions of the deep south for millions of years, is warming. The rate of warming in the Southern Ocean has exceeded the global average. The sea ice that forms and retreats around Antarctic edges each year. The foundation of the food web that sustains krill and penguins and seals and toothfish and whales is forming less extensively in some sectors than it did decades ago. The patterns are shifting in ways that are not yet fully understood, in ways that may not be understood until the damage is well underway. Antarctic krill are small, a few centimeters long, transparent, abundant beyond easy imagining in their billions of individuals. They graze on ice algae, the microscopic plants that grow on the underside of sea ice during the Antarctic winter. As the extent and duration of sea ice declines in parts of the Southern Ocean, the ice algae decline with it, and the krill that depend on ice algae for a portion of their winter diet face a reduction in food. Krill are not at the bottom of the food web. They are the food web. Almost every large animal in the Southern Ocean depends on them. The colossal squid does not eat krill directly. It eats toothfish and other large prey. But the toothfish eat krill. The seals and penguins that eat smaller squid eat krill. The entire ecosystem, at its foundation, is built on those small transparent creatures and the ice they depend on. Pull the ice, and you begin to pull the foundation. And then there is the other thing. Microplastics have been found in the sediments of the Southern Ocean at depths that should, by any intuitive logic, be too remote and too deep for surface pollution to reach. They have been found in the bodies of krill, in the gut contents of deep-sea fish, in the tissue of seabirds that nest on Antarctic islands, and that never approach a human settlement in their lives. The ability of our discarded material to find its way into the most remote ecosystems on Earth continues to outpace our ability to fully account for it. We do not know what microplastics mean for the colossal squid specifically. We have not examined enough specimens, and those we have examined have not been subjected to the kind of detailed contamination analysis that would answer the question. What we know is that depth, distance, and cold do not constitute protection. The squid lives in water that is connected, through circulation and current, to the surface of the global ocean. Whatever is in the surface ocean eventually reaches the deep. The colossal squid has survived every extinction event of the past several 100 million years. Its ancestors were in the Mesozoic oceans when the dinosaurs walked the land. It survived what the dinosaurs did not. It is not fragile by any ordinary definition of the word. But it has never before shared its ocean with us. Return to the eye for a moment, the 27-centimeter eye with its internal light source, in water where no sunlight reaches. What does the colossal squid actually see? The world at 1,000 meters is a world of blue. Not blue like a summer sky, not blue like a tropical shallow, but a very specific and very faint blue-green that is produced by bioluminescence. It has been estimated that up to 90% of the animals living in the mesopelagic and bathypelagic zones produce some form of bioluminescent light. The water at this depth is not uniformly black. It is intermittently and irregularly lit from within by the living things moving through it. These lights are not bright by any standard we would apply to brightness at the surface. A bioluminescent flash from a small dinoflagellate is a single photon or a handful of photons in a volume of water the size of a marble. A larger creature, like a lanternfish or an anglerfish or a siphonophore, produces something more sustained and more detectable, but still dim by the standards of anything we would call light in the world above. A 27-centimeter eye, open to its fullest extent, collects light the way a satellite dish collects radio waves, across the largest possible area, concentrating everything the dark offers into a single point of focus. The lens of the colossal squid's eye is, by the mathematics of optics, extraordinarily sensitive to bioluminescent signals that a smaller eye would never register. Where a human eye at this depth would perceive complete blackness, the colossal squid perceives movement and shape, and the cold signatures of living things. The hypothesis about the internal photophore suggests that the squid also illuminates targets at very close range, the way a deep-sea predator with its own light source can momentarily reveal what is directly in front of it. The squid may live in a world that is almost completely dark, except for the very near field, the area within a meter or two of its own eye, where its internal lamp creates a small cone of visible information. And then there is the sperm whale hypothesis, that the eye's primary function, at the scale and sensitivity it has achieved, is to detect the bioluminescent wake of an approaching predator at a range that gives the squid time to respond. A whale moving through bioluminescent water leaves a track behind it, a trail of disturbed organisms lighting up in sequence like a runway. An eye built for this purpose, sensitive to the faintest disruption in the light field around it, would see a whale coming long before the whale came close. The colossal squid does not experience the world the way we experience it. Its world is built of faint light and slow cold, and the chemistry of ammonium chloride, and the weight of 100 atmospheres pressing on every surface of its body. Its world is ancient and consistent and largely unchanged for millions of years. The eye it opens in that world is reading information we cannot access, processing a version of the deep ocean that we have never been equipped to perceive. We have held the eye in our hands, we have measured it, We have stared into the lens the size of an orange and tried to understand what it sees. But the eye, even removed from the animal, gives nothing away. We began with an eye watching from below. We end in the same place, because the colossal squid has not moved while we have been descending toward it. It has not changed while we have been learning about it. It has been down there at 1,000 meters in the Ross Sea and the Weddell Sea and the cold waters that circle the Antarctic continent, drifting and waiting and watching, entirely indifferent to the fact that we have named it and measured its dead specimens and photographed its eye. Consider what we have not done. We have never watched a colossal squid hunt. We have never filmed one mating. We have never seen a live one in its natural depth, in the water it belongs to, moving the way it actually moves. Everything we know about this animal comes from the dead and the dying and the fragmentary, from beaks in whale stomachs, and specimens hauled up in fishing gear, and a frozen animal examined on a laboratory bench in Wellington. The picture we have is a picture made entirely of edges. The interior of the life remains unseen. This is extraordinary. We live in an era when satellites map the surface of distant moons in detail finer than a city block, when submersible cameras have photographed the bottom of the Mariana Trench in high resolution, when almost everything that lives in accessible water has been filmed, catalogued, and described in considerable detail. And yet the largest invertebrate on our own planet, living in our own ocean, has never been observed going about its actual life. The colossal squid does not need our observation to exist. It has been existing, in various ancestral forms, for hundreds of millions of years before the first human eye appeared in the world. It will, if we leave its ocean in reasonable condition, continue existing long after the last human institution that studies it has been replaced by whatever comes next. The squid is not waiting for us to understand it. The squid is not waiting for anything except prey and the slow cold passage of time in the dark. What we need the colossal squid for is something different. We need it as proof that the world is still larger than our instruments, that the ocean, which we have mapped and fished and polluted and traversed for centuries, still contains a life we have never witnessed, that there is an animal the size of a small car, with the largest eye in zoology, living 1,000 meters below the surface of the sea. We think we know and conducting a life that is still completely private. The unknown is not a failure of knowledge. The unknown is the assurance that the world is inexhaustible, that there is always something else to find, always another layer beneath the layer we have reached, always a kind of life being lived that has no need of our attention, but that makes the world we thought we understood seem larger by a factor we cannot easily measure. The eye is still down there, still open, still turning slowly in the dark toward whatever approaches. It does not know what the world has shown us about it. It does not know we have been descending toward it all this time. It waits, it watches, it keeps its secrets in the deep, and the deep, as always, holds its own